Online.
Okay. Good afternoon, everyone. Welcome once more to another seminar of our cycle of seminars of the astronomy department here in IAG. And many thanks for joining us. And if you are joining us also on our YouTube channel. And today's speaker is Professor Néstor Espinoza. So Néstor, many thanks for accepting our invitation and to be here with us today. And just let me briefly say that Professor Espinoza got his PhD degree from the Pontificia Universidad Católica in Chile and have worked in the Max Planck Institute in Heidelberg in Germany. And currently he's an assistant astronomer at the Space Telescope Science Institute. And his research is focused in the detection of new exoplanets, the characterization of their atmospheres, and the understanding of how these worlds came to be. And today, Néstor is going to talk about constraining the atmospheric composition of mornings and evenings on distant exoplanets. So like always, please turn off your microphones and cameras during the talk. And if you have a question, you can raise your hand here in the Google Meet, or you can write it down in the YouTube chat, and the questions will be asked after the talk. So Néstor, whenever you are ready, please, you can start.
All right. Thank you very much, Maria Victoria. It was a really
welcome.
nice intro, and very happy to be here. It's a pleasure for me to be able to present this very neat work that we've been doing with a ton of folks and collaborators. So let me start sharing my screen. And you should now see my slides.
Yes.
That's okay? Yeah. Okay. Awesome. All right. Yeah. So I'm going to be talking today about constraining the atmospheric composition of morning and evenings of distant worlds with TESS and JWST. And as you see, there's different words here, like morning and evenings. What do I mean by that? Probably many of you are asking. And what this has to do with TESS and JWST. So it's a pleasure for me to be able to present the work that we've been doing on this. And of course, this is not work that I've been doing alone. This is work that we've been doing with a ton of folks all over the world, including people from here at SDSCI, Lauren Miller, a science super analyst working with me on this project, Catherine Jones, that she's a grad student at the University of Bern, Jayshin Patel from the University of Stockholm, and many other collaborators from the Max Planck, Leuven, even here in the Space Telescope, NASA, and Hawaii. So let me first, before going into atmospheric characterization of the morning and evenings, let me ask the question of why do we want to constrain these atmospheres, and what does that has to do with morning and evenings? The very first question, is why. So right now we're in this, I call it the golden era of exoplanets, because we just reached, I think a couple of weeks ago, the mark of more than 5,000 exoplanets discovered by humanity. See, this is the number right now of exoplanets that we know that are confirmed as of today. And we have this huge sample right now that we can just take it and start exploring the really big questions about exoplanetary science and planetary science, like our own solar system over here. Questions like how are planets formed? What are they made of? What are they, do they have your favorite element, even if there's life out there? And how do we, our solar system, how do we fit into this picture that we see in other planetary worlds? And actually, you don't have to go that far, like to distant exoplanets, to start seeing that there's a huge diversity on this atmospheric composition, which was the first topic in the title of my slides. On the diversity of atmospheric composition, you can just look at the planets in our solar system to actually realize that it's a very, very diverse environment. So here I'm plotting. This is one of my favorite plots ever. This is a plot by Trajan collaborators in a book/report from 2018 called Saturn in the 21st Century. And what I'm going to be showing is in the x-axis, I'm plotting the different elements. Like you can choose your favorite, maybe carbon, oxygen, you name it. And in the y-axis, I'm going to plot the planetary to protosolar elemental abundance ratios. So that means what is the abundance in these planets of these different elements as compared to the seeds, the protosolar elemental abundance, how the elements looked in the protosolar environment. So if you believed, for instance, that all these planets just form directly from these protosolar elemental abundance and just condensed out, and that's it. You should expect for all the elements to be like at a ratio of 1, right? If these seeds that were around were the ones that this planet just accreted, then they should have the same elemental abundance as the protosun, of the protosolar elemental abundances. But when you start looking at the actual, measurement from these different planets in the solar system, you start figuring out that that's actually not the case. And actually, just starting with Jupiter here, Jupiter is actually enhanced in the elements, like in every one, almost all of the ones that you're seeing here, except for oxygen, which there's a story behind this, and I think this has been reanalyzed with Juno right now, and this is up where you see the orange band here. You see that it's enhanced by a factor of like 3 to 4 over solar, over the protosolar. And if you keep going to the planets in the solar system, from the most massive, which is Jupiter, to the less massive, you start seeing that they start getting more and more enriched. So Saturn is like 10 times more enriched, and Uranus and Neptune is like 100 times more enriched. You might be wondering, like, why? Like, why are they more enhanced in these elements? Well, actually, this is expected from co-accretion, from the co-accretion scenario. And co-accretion states basically that you form a core, which is like a rocky core for these giant planets. And there you start accreting gas and solids from the protosolar nebula. And that's what kind of elements and how much do you acquire depend a ton on your mass. In particular, the more massive you are, the less enriched that you are. And this is exactly what you see in the solar system. Like the most massive planet, Jupiter, is the least least enriched of all the planets. And actually, we are in this golden era of exoplanets, in which we can start doing very similar analysis to these ones that has been played in the literature in the past like 40 to 50 years. We can now start doing the same thing with exoplanets. And this is like the beauty of being working on this field right now. We can start asking what's the diversity of enrichment in the galaxy, or at least in the planet that we can actually see. So what I'm showing here, what I'm going to show is the planetary mass. It's a different plot, but it's the same information. The planetary mass in the x-axis, and I'm going to show basically the metallicity, if you want it, in the y-axis of each of the planets. And you can see, so here's the trend of the solar system. Again, the more massive you are, the less enriched you are. So to the right. And we can actually start doing similar analysis to exoplanets. And you see points with larger errors, like I give you that, in comparison to the solar system, which is indicated here by letters. This U, N, S, J are indicated here. And all the rest of the points are exoplanets. And the different colors measure what we have used to measure that enrichment. So you see that most of the points are blue points, it's water, which is what we can see with the Hubble Space Telescope, mainly. But there's also potassium and sodium with orange and red, and even methane constraints from some of the direct. So for the solar systems, planets in particular, we have not measured that from exoplanets. And one thing that you can see directly from this, so this is a beautiful work made by Luis Wellbanks and collaborators in 2019, in which he fitted the trend that you see in exoplanets and the trend that you see in the solar system, and they're different. They're scale different. So the orange line with error bars does not match the blue line with error bars here. So the big question is why? Why? I mean, we were expecting them to be more or less similar, but they're not. So there's many questions that arise from here. So maybe one solution could be formation. Maybe the planets in the solar system form different from the exoplanets that we study. That might be the case because, as I'm putting here, the exoplanets are mainly close-in hot giant planets, so planets the size of Jupiter, that are orbits that are closer than the distance to Mercury in the solar systems. They're very, very close in. They have like a different formation scenario probably than the planets in our solar system. So that different formation might give rise to a different trend. Could it be our models as well? Maybe we're messing up our models for actually characterizing the atmospheres of these planets. Could it be clouds as well? So we see that these exoplanets are very cloudy, even though we see like a ton of these close-in planets are very, very hot, like temperatures even exceeding 2,000 Kelvin, because of the radiation from the star. They also form clouds. There's like clouds of metals in this planet. Like it's mind-blowing. Or could it be, the elements? So again, as I told you before, the plot here for the orange line is mainly made with methane, whereas for the exoplanets, we're measuring with different elements, and maybe different elements give different trends. The quick answer to all this is that we have not reached like a consensus on this. We don't know what might be happening. And there's one line from all the possibilities. There's one line that I got very, very interested a few years ago. And this story actually started with a conference/workshop that I went. This was in 2017, I remember. And it was a conference in which or a handful of the exoplaneteers that are dedicated to atmospheric characterization, they were all invited to a meeting. And we gave talks and we spoke with each other. And I remember one talk by Christiane Helling from the University of St. Andrews, that at the start of her talk, imagine the scenario, experts in atmospheric characterization in the crowd, and she goes in front of everyone. And before even starting her talks, she says this phrase, I want to start my talk saying that I don't believe there is one water abundance or any elemental abundance to extract from hot giant exoplanets. So her point was that giant planets, or planets in general, are 3D objects, right? So there's not one abundance that you can get, but there's these different abundances depending where you look at. And the whole point of her talk was actually making that the case. And I'm going to show a plot, and a couple of plots, and a couple theoretical and actually evidence from data that actually show that this actually is the case. She was totally right, of course. So in order to understand why this might be a problem for atmospheric characterization, I have to introduce you a little bit into how do we do most of this exoplanet characterization? How do we actually measure these abundances that I was telling you about before? And we do this mainly through a technique which is called transient spectroscopy. The basic idea is that the atmosphere that is around the planet interacts with the star once it passes in front of the star. And we measure these transits as a function of wavelength, such that whenever there's one element that absorbs a ton in the atmosphere, then you will observe a deeper transit. So imagine, for instance, that you observe just at the wavelength of water in which water absorbs. And then at that wavelength, if the atmosphere is filled with water, then most of that water will absorb the light and you will observe a deeper transit. And what we do actually in practice is to measure the transit depth as a function of wavelength. And then whenever we see a peak, we see an enhancement, then we see a larger, we imply a larger radii, and we imply something is absorbing at those wavelengths. And this is the technique of transient spectroscopy. So the main idea is something like this, the toy model for transient spectroscopy is this one. So you have a star, you have the planet's atmosphere, and then the planet atmosphere it has a different size as a function of wavelength. And then you measure this transient spectrum, the transient depth, that's a function of wavelength. And then whenever you see peaks, then that's an element. It can be sodium, potassium, or water, the ones that I was just showing before. This is the toy model that we all been assuming for years, right? And because it's easier, because it's easy to model, you just, it's a circular planet passing in front of the star. There's analytical formulae for that kind of problems. So it's easy to fit to data and to extract and to interpret information. But here was Christiane Helling, right, giving her presentation, and he presented early work on this plot that I'm going to show right now. So this is from her paper, 2020. Of course, these ideas like this have been brought up even before 2020. There's a paper from Jonathan Forney in 2010 that actually hinted at this directly from 3D model atmospheres, but didn't delve into much detail, as much detail as Christiane Helling did in this plot that I'm going to show, and many other authors, as you can see here in the list. But the main idea is the following. So just look at the left plot. The left plot is the gas temperature in a slice. So what I'm doing is what Christiane was doing. Sorry, she was cutting through the planet like this, and then trying to detect she has a tree modeling framework, and trying to tell you what the temperature of the gas in the atmosphere is at different parts of that cut. And as you can see, there's a lower temperature in the morning Terminator. We call this, by the way, morning and evening, because we assume the planets rotate more or less at the same period as the planet, because they're tidally locked. So they're most likely tidally locked. So the most common outcome of that is that most of the time the planet has a constant day side looking at the star, but that means that the planet has to rotate at the same period, just as the moon, right? The moon also has a rotation period, which is the same as very similar to the orbital period. These hot giant exoplanets is the same thing. They're so close that they are tidal locked, and this is the most common outcome of that. And then the morning terminator we call the part of the planet that is rotating from the night side to the day side, right? So it's constantly showing that part. And the evening, which is again a constant evening. So that, that's the deal of living in a hot giant exoplanet. Like, you don't want to live here because you have constant mornings, constant evenings, and constant day side and night sides. But that's the future for these planets, anyways. It's not for us to judge. So the evening is the part of the planet that goes from the day side to the night side. So in the morning, from the night side to the day side, you see that the temperature is much lower. They can reach temperatures as low as like under 1,000 kelvins. Whereas in the evening part of the planet, you see that it's hotter, right? It can reach temperatures of above like 2,000. And the whole idea of this and how they arrive at this is it has to do with the fact that there's evidence, ample evidence, that there's dynamics in these hot giant exoplanets. So there's so much energy going in that there's winds, there's material being brought from the day side to the night side, because there's a huge temperature difference, right? So you have the night side like below 1,000 kelvins, and then you have the day side constantly being bombarded by radiation, temperatures around 2,000 Kelvin. And this temperature difference produces, a gradient. And that gradient moves energy, moves material, etc. So that's the explanation of why we're seeing different temperatures at each terminator. The central panel shows the nucleation rate, like how easy you can form clouds. So the reddish, the more easier you can form clouds. So here it is showing that she's predicting basically that you're going to have clouds in the morning. It's going to be cloudy mornings in these hot giant exoplanets and cloudless evenings. And in the right panel, you see the water abundance, which is what we measure typically for transient spectroscopy. And the plots that I showed you before, most of the points were water abundances. And you see that the water abundance also changes by a factor of 2, actually, between the morning and the evening. So these limb differences, these differences between the morning and the evening, you cannot just pass them under the rug and say, like, we're gonna assume the planet is perfect. Well, it's not. Like, newsflash. Of course, this is not like, oh, newsflash. It's an astronomer's black hole. Exoplanets are in fact 3D. Of course, we know that there are 3D objects, right? But the issue right now is that we don't know how big of an impact this has for transient spectroscopy, for instance. And that's the point that Christian Helling and others have been doing. Like, from theory, it seems like it's a big deal. Can we observe this? That's the big question. How big is this effect in reality? Is the big question. And this is like the main motivation. Like, this question here, the main motivation that led me to work on this and to lead a team that is doing this kind of work to actually measure how big this effect is in reality. So what we're doing, we're starting with a very simple toy model for measuring this directly from transit lightcurves. And the main idea is that, as Christian Helling was showing, the morning and the evening terminators, they're different. They have different effective sizes, actually, because you measure different abundances, different temperatures. So the sizes should be different between morning and evening. So if we could somehow extract the spectrum from the morning and the evening and plot it and then measure directly if these abundances are as different as these models are predicting, then that would be like a huge slam dunk. It would be awesome to say, like, yes, this is an issue, or no, this is below X, and therefore we don't need to worry that much about it. Models predict it should be an issue. So we want to go and measure this. That's the main deal. So we sat down with a bunch of experts to actually measure this. In our team, for instance, we have Ludmila Caron and Paul Mollier, which are experts on 3D modeling and actually passing those 3D models to transient spectroscopy to see how this should look in the actual data. And as you can see, here's one of models of Ludmila Caron, in which she's showing basically the temperature pressure profile. So this is the right panel. The x-axis is temperature, the y-axis is pressure, and you see it's increasing downwards because we use it as a measure of the height. The deeper you are in an atmosphere, the more pressure you have, and the larger is the column of material on top of you. So this is measuring, pressure temperature of both the evening terminator in gray and the west Terminator or the morning Terminator in yellow, which is a little bit colder. And so once we have these 3D models, we pass them to Paul Mollier, which computes like transient spectroscopy out of this, and we see that this should create large differences. Like here in yellow again, or orange. I guess my palette of colors in my eyes is not very good. Orange is the morning Terminator, and gray is the evening Terminators. And you see that they produce different spectra. So you should be able to measure this, at least with the precisions that we're gonna have, and we're already having some instruments. But yeah. So also all this depends on ton of the cloud properties of the evening and mornings. So this whole thing is very promising, because if you could measure this, if you could measure the spectrum from the evening and in the morning, then you can tell stuff like, oh, yes, the morning is cloudy and has X amount of clouds. The evening is not, and the upper limit of those cloud levels is like Y, and stuff like that. You can actually do like 3D predictions and observations of exoplanets with this technique, which would be completely amazing. Okay, all this, I hope that I could have like put all this excitement on the spot. And now the big question is how? How do we do this? Like, all this sounds great, but Néstor, how are you gonna do this, like in practice? So the first thing that we did is that we sit down with the amazing Catherine Jones, again, PhD student from the University of Bern. It was a total pleasure working with her. We work to this day with her, but we work on this paper together, this set of papers together, and on a software that could actually model these asymmetric limb light curves. So the main idea is that you can have not only like the evening and morning Terminators that have different sizes, but that could actually be rotated as well. Because, one thing is the orbital motion, but the planet might have its own axial tilt. In fact, our own planet has an axial tilt. So we wanted to model this to create a software that you could model light curves that are like this, like they're asymmetric and they're like tilted. And that led to Catwoman. So this is the software that we created. It's it's documented. You can pip install Catwoman, and you may be wondering like, why you name it Catwoman? There's no big reason, to be honest. Catherine led the development of this, and Catwoman, Catherine, made sense. Not that part, but the part that we were mostly motivated though has to do with the fact that the most used software to computing light curves, it's called Batman. It was created by Laura Kreidberg back in 2015. So we wanted to keep the the superhero theme, and that's where Catwoman came from. It's not an acronym, by the way. It's just a name. So here's a showcase of what it can do. So it can model these asymmetric light curves, and it can account for this axial tilt. And here we're computing like a simulation of a light curve with a precision similar to what you will get, like slightly worse actually, to what you would get with JWST, with the James Webb Space Telescope. I'm going to mention it in a little bit in case you're aware of what's going on over there. But we're going to get this kind of precisions very soon. And we can actually, most of the impact of these asymmetric light curves happens between ingress and egress, like when the planet is just touching the star. That's what these are marked over here. And the amplitude of those changes can be, as large as 200 to 300 parts per million, which is totally measurable with today's technology and with future technology for sure. So we wrote a paper, this Espinoza and Jones 2021, last year, with Catherine, on actually doing simulations on what we could do with this. And the big question, one of the big questions that we had is that can we detect this with JWST, with the James Webb Space Telescope? In case you're not obviously the news with the James Webb Space Telescope, this telescope was just launched on December 25th last year. I was chatting with some colleagues, like kind of the best Christmas present. I think I don't remember being that excited about a Christmas since like I was a teenager, perhaps. So very timely analysis, the one that we did last year with Catherine, given that the telescope just launched. Here's a picture in left of the rocket, JWST, and then the folks at Arianespace, the folks that got the rocket up and put Webb in its excellent orbit towards L2. They had a camera on it, and they took a picture when Webb detached from the rocket that you're seeing in the right, which was absolutely stunning. Where by the way, right now we're undergoing commissioning. I'm participating in that commission. It's been a privilege to be part of that. And as you've been hearing from the press, everything's going beautifully. This telescope, it's amazing. So we started looking into, how these limb detections could happen with JWST. And some of you might be wondering, why don't you do it with our already built telescopes like HST, like the Hubble Space Telescope? And doing this kind of analysis with the Hubble, it's kind of tough because Hubble orbits around the Earth, and this create light curves gaps. They create gaps in the light curves. So you remember that we were trying to measure these little dimmings in ingress and egress, and this lasts like 20 minutes. But HST, the problem, because it goes around the Earth, there's a portion of the time while observing an exoplanet in which it just cannot observe, and this is right here. So this is indicated by the red arrows. There's some gaps in the light curve, which are like, they kill the possibility of measuring this in most exoplanets. There's a handful in which we could do it, but it's tough. It's really tough. So that's why we went with JWST. And so what we did is that we said, okay, let's assume that we don't know anything first. Let's assume that we know some stuff. And then let's also assume that we know everything about this planetary system. And see in these three cases, what's the detectability of the effect? So this is the maps that we made. I call them detectability maps. And then the x-axis, you see the morning to evening depth differences. So the differences between the transit depth that the morning produces and the evening produces. So to give you an idea, this goes from like 500 all the way to 5 parts per million in the x-axis in the top. But people have been predicting that you could measure like very large differences, like in the order of 1,000 or 2,000 parts per million. And in the y-axis is light curve precision. To give you an idea on that, this goes all the way from 10 parts per million all the way to 1,000 in the bottom. JWST can reach tens of parts per million. Missions like TESS or Kepler can reach like hundreds or 200s per HST as well. And ground-based observatories can reach like 500 to like 1,000, maybe going down to 2,000 parts per million. That's like the order of magnitude. So what we did is that we did like a ton of simulations versus like symmetric and asymmetric light curves. And then we compared, how much detectable these asymmetric light curves would be in this precision. And we compared this to the log evidence. I'm not going to go into the detail, but the thing that you need to understand is that the bluer, the better. The bluer, the better. The bluer is the most detectable. So Catwoman wins with blue, and Batman wins like the asymmetric light curves. Like Vu is the whiter colors. So if you know everything about the system, there's a region of detectability here. This is for hot Jupiters, by the way, for giant planets. That covers both the planet precisions like TESS and all the way down to JWST. So this is totally detectable in that case. If you don't know, in this case, limb darkening, which is the middle one, limb darkening is important. You might be wondering why. Limb darkening is a stellar thing. Why does this matter for the planet? And it matters because the curvature of the transits that you've been seeing in these pictures that I've been showing, that's given by limb darkening. So the first question that I had, like, well, we don't know limb darkening very well. Like, I don't trust the model that much, at least. So I was wondering, would this make an impact? And even if you're completely ignorant about limb darkening, you still have the same detectability value, which was great. However, all the detectability like goes down to 0 if you don't know the time of transit. And that's very important because if you shift the transit a little bit, then you can create very similar bumps to the ones that I was showing for the asymmetric light curves. However, for JWST, this is not an issue because you will measure the transit light curves as a function of wavelength. So different wavelengths, they all have the same time of transit. So you can constrain that extremely precisely, and that shouldn't be an issue. So the last panel is not applicable for JWST. We actually did some simulations on what JWST would be able to observe, and we actually would be able to get spectra from their evening limbs and the morning limbs. Like the dream that I was telling you before, this is doable with JWST. This is what we're showing here. So the x-axis is wavelength, y-axis is the limb depth for the evening and the morning terminators. And we can actually retrieve you, that's the right panel, the temperature pressure profiles of each side of the planet, which is completely mind-blowing. Like this is something that I was not expecting for it to be that good. We actually have a pilot program to constrain this in JWST, in cycle 1 JWST. We have a proposal accepted. It's going to be observed next year. So, keep your eyes tuned for that beautiful spectra that we're going to be able to get with that. The next question was could we do it like right now? We, Catherine and I were like getting pretty anxious. Like, can we detect this like right now with missions like TESS? The Transient Exoplanet Survey satellite, which is observing the entire sky. There's beautiful, beautiful light curves. I'm going to show them in a minute of exoplanets that you could actually constrain this whole thing. And here's the detectability map for TESS. Like even, and this is the case in which even when you don't know, you're completely ignorant about the time of transit. And the reason is that why it doesn't impact in this case is that TESS observes many, many transits for a lot of exoplanets, like, tens to hundreds of transits, because it's observing continuously in some regions. So you can get like very precise measurements of the time of transit together with these limb asymmetries. So we did a pilot program on all this with a student, Jaishal Patel from the University of Stockholm, on actually just modeling the light curves of TESS to get an idea on what the precision of this is. And this actually, it's a paper that was just published this year. We analyzed actually limb darkening, the thing that I was speaking to you before, and how well limb darkening, we predict limb darkening from these beautiful transit light curves that we get for these exoplanets. Turns out that not that well, so you have to be careful. But we get beautiful, beautiful light curves. Like the transit depth precision that we get on these light curves, it's in the order of 30 parts per million per subsistence. Like this is what you're seeing there. This is completely crazy. Like this is JWST kind of precision in the transit depth. So TESS, it's an amazing instrument. It's a small instrument. Like it's a like a 1 meter thing. It has little cameras on it that are smaller, but it's a very powerful instrument. So if you want to check out more of that work from Jaishal, that paper was really nice. You can totally check it in the archive. It was published like a couple of weeks ago. But here's one of these light curves in which we would just put all the data together and we phased it around the transits. As you can see that the light curve, it's absolutely stunning. It's like textbook level light curve, and the scatter on the data points is 70 parts per million. So what we did, Jaishal got an initial idea on the precisions, and we analyzed other effects like the darkening. And now we're working with a science support analyst here at Space Telescope and actually fitting these Catwoman models to these light curves. And we're actually constraining right now morning and evening. So this is one of those constraints. This is an early plot actually of this. Now the precision is much better, a factor of 2 better. But in an early plot of this, once we were starting the project, we were able to measure, that we can constrain the morning to evening depth differences to even better precisions than what you're seeing here. So this is work by Lauren Miller. She's working with me here at Space Telescope, and she's been actually doing some amazing work on this. So, and the thing that I'm going to show is work in progress. But with these TESS light curves, we're able to constrain the morning and evening limbs and put this in this spectrum that I was showing you before, like the simulations for JWST. So what I'm going to show now is like in this plot, it's going to be in the x-axis, the wavelength, same thing. In the y-axis, the depth of the limb of the evening and the morning limbs. And with previous work, anything on this range could be possible. Like there was a range of 2,000, even authors predicting that you could go all the way to 5,000 parts per million, way beyond the limits of this plot. And for WAS62, in this case, for this planet, we were able to constrain this limb differences down to this level that you're seeing here. So those are the data points. There's some correlation between those data points, by the way, that you're not seeing in this plot. It's hard for me to show it. But I'm showing here the models that we run atmospheric retrievals on top of this. And the models actually constrain the limb differences to be like around 300 to 400 parts per million. And that's a huge constraint. This constraint has not been done before, to my knowledge, on any data set. So this is this kind of amazing work that Lauren is doing. She's been analyzing like basically every TESS light curve, but we're focusing on the most promising ones. And we have been seeing in like constantly that most of the systems, there's always a larger evening than the morning. So for all the systems that we've been analyzing, that's the case. So it seems that, and this is the population level analysis that we're planning with Lauren, is that it seems that you could plot like the morning to even in depth difference as a function of the equilibrium temperature. And I would expect a figure like this, in which for the coldest planets, the planets that have lower equilibrium temperatures, you'll have like uniform cloud cover, because they will be very, very cloudy, and there wouldn't be much difference between the morning and the evening. But then for the hotter planets, you're so hot that you should not have condensation. So the evening and the morning limbs should be more or less similar. But then there's a sweet spot in between that we're trying to uncover, what that temperature is, in which maybe there's this maximum morning to evening depth differences. I'll let you know once we finish this work with Lauren. but this is ongoing, and it's been pretty exciting to see all these retrievals happening with her work. So, as a summary, the first point is that there's might not be only one gas abundance to extract from transient exoplanets. Of course, it's an insight that has been brought by several authors, but to my mind, the most stunning one was when Christiane Helling said this in top of an audience. And we need this for planet formation insights. Exoplanet limbs might be key. They're very nice windows for 3D pictures of exoplanets, and they're also cheaper. This is something that I did not mention, but there's ways in which you can get 3D information of exoplanets, in particular doing phase curves. That is, following the flux of the planet as it goes around the star, and as it starts showing you the day side. But that's very expensive. You have to spend like days on an exoplanet with your telescope. In this case, this 10 billion telescope that's going to be JWST. But analyzing the limbs in the way that we've been doing it with TESS, and we're going to do it with JWST, you can do that with like a few hours. So you just need a few hours to observe the transit, and then you get 3D information out of that. Again, current and future data. Actually, with current and future data, these things might be observable, and TESS could provide the first insights. In fact, with this board that I just showed you, we are providing the very first insights into the how big this effect is. So we're attaining the objective that I told you at the very beginning, and anyone can do it. That's the most beautiful part, I think, of all this. That we got a library that it's open source, CanWoman, with which you can feed your own asymmetric transient lightcurves. And that would be it. So I hope that this made it clear that constraining morning and evening limbs of exoplanets, it's very exciting. It's something that's happening, and it's something that we're very excited to keep sharing with everyone in the community.
Okay, great. Thank you very much for this very clear talk, Néstor. Many thanks. So let's see if there is open. Let's open for questions. I see Reinaldo. Would you like to start?
Néstor, thank you very much for the talk. It was very clear. I have a basic question about how you get the temperature profile is by the widths of the lines of the transit spectrum. Is it so?
So the question is, how do we measure the temperature pressure profile?
The temperature profile, yeah.
Yeah. So the main idea on this is that, right, so once you get a transit spectrum, you run a retrieval on top of that. And then the whole idea is that different depths are going to give you different information at different wavelengths. So, pressure, it's like related to wavelength in some complex way. And we put all that complexization, just build it into an atmospheric retrieval tool. So what we do is that we compute many of those models, and then we try to find the best that fit the actual data. And there's only a range of temperature pressure profiles that are consistent with the data. And those were the ones that I was showing here.
Thank you.
Well, I think next is, I'm really sorry, I cannot see the, Reinaldo, can you see who's next?
That is next.
Sorry, Betty, please, go ahead.
Hi, Néstor, thanks a lot for this very nice and clear talk. Very, very interesting. And so let me ask you one thing about because you have this in the beginning of the presentation, you showed this diagram that there is, the solar abundance versus exoplanet, other exoplanets, the solar system abundance versus the exoplanet abundance, and there is this, it's systematically smaller, right, in the case of exoplanets. But this, my understanding is that this should be due to observational bias. Isn't that so? Because actually the planets, the exoplanets that we are able to observe are still the bigger ones that are more like Jupiter's and giant or gaseous and less massive planets. So in this case, we might expect this difference in the average abundance. Isn't that so?
I'm not really sure. I mean, the fact is that our planetary formation models right now, even for the hot Jupiters, they all form and they all accrete their atmospheres very early, like below a couple million years. And that means that, and once that happens, then you have this migration to the interior orbits that occurs like in timescales that are longer than that. So in theory, just based on our models for planet formation, in terms of accretion of an atmosphere, you shouldn't expect like a large difference between like how Jupiter formed and what some of these hot Jupiters formed. But I do agree that there's other details going around. Like we are not considering the fact that the abundance, like the proto abundances of these other systems are different, that the solar system, like we might have some biases in which system we're observing, because most of these points that you saw, those are planets for which we can perform atmospheric characterization, and that has a brightness bias on it. It's some sort of a Malquist kind of bias in which we only follow or we only perform atmospheric characterization so far on the brightest exoplanets. There might be a bias there, for instance.
Right.
There might be a bias also that, although I said that our models are pretty similar in terms of accretion, well, our models might be wrong. And in fact, Yamila Amiga, we were just speaking about her at the very beginning. Yamila has some models, and I've been working with her on this, in which some planets might accrete their atmospheres a little bit inwards, like inwards to the ice line, to the water ice line, which is where, beyond which it's predicted that Jupiter and the other planetary systems in our solar system formed. So there might be some biases. I totally get that. Yes, that might be a thing. And also the thing that has stuck in my mind as well is that the chemistry might be totally different between the solar system and these giant planets, because as you said, for most of these giant planets that we examine from the exoplanets, those are close in, very hot. They have like an extra addition of energy, and the chemistry on those atmospheres might be totally different to what we see in the solar system, which are like very far away, very relaxed, relatively speaking. So there might be several lines on why this might be so.
Okay, yeah, I do agree with you. Thanks a lot. Very nice talk again.
Okay, let's move on to Jorge.
Hi, Néstor. Thank you for the talk. And I am curious about how you're dealing with the stellar limb darkening. You mentioned that it could be a problem in your analysis.
Yeah. So one of the things that we showed is that even if you're ignorant about that, then it shouldn't be such a big issue, because limb darkening should be a symmetric thing. Fingers crossed. So in that case, so how we're handling is that we're just exploring the entire parameter space of the limb darkening coefficients that you could fit. But yes, we are using a simplistic law, in this case, like a quadratic law or a logarithmic law, a square root, and not going full-blown nonlinear with a 4-parameter law. That might be an issue for some systems, especially the ones that are close to grazing, like in the edges of the transiting the edges of the star. But that's how we handle it so far. Again, I'm not too convinced that we know limb darkening to a level of precision to the ones that we need here, and that's why I prefer to keep like ignorance about this whenever I do fits on transient lightcurves. And I think Jay Shill's paper that we published earlier this year actually shows that with TESS. So we do see offsets of the limb darkening coefficients that you would get, say, from tables against the ones you observe on the data. And that's especially true for colder stars, like for M dwarfs. Like you see that they go off like this, and that makes sense, right? Because everything has been calibrated against the sun. So yeah, that's my take on limb darkening. So we're very ignorant of the light curve fitting, so I don't think it's an issue. But if you're gonna fix those limb darkening coefficients, you're gonna trust the models, then you have to be careful, I think, and that can give rise to biases for sure.
Okay, thank you.
Okay, so Reinaldo, please.
Néstor, I have a curiosity. So do you predict some maximum contrast in density between the morning and evening side of the planets based on, I don't know, maybe in the circulation pattern of the atmosphere? Because I understand if the contrast is too much, there will be circulation trying to reduce the gradient of the temperature. So do you expect some maximum contrast.
So are you asking where do we expect this maximum contrast between morning and evening, given all we know about like
Yes.
3D dynamics of exoplanets?
Yes.
Yeah, that's a very good question. Yes, kind of. The truth is that whenever I've asked like 3D modelers, they're like very skeptic about translating global properties like the ones that we've been observing in phase curves, so these flux changes as a function of orbital phase, to tiny changes in the morning and evenings, because there's clouds involved. And whenever you have clouds involved, the way in which 3D models work is that you implement those later, like in a post-processing step. So first, you leave your 3D world going around, and it has its temperature and its chemistry, and you assume there's no clouds. And then at the end, with the temperature pressure profiles that you have across the entire planet, then you like paste clouds on top of that. But then there has been works recently, like last year, a couple of years ago, from Emily Rauscher from the University of Michigan. She's been one of the first to implement feedback on clouds, like 3D models with continuous feedback from clouds. And that changes the picture kind of like by a lot. So whenever, after that work, but also before that, whenever I ask 3D model experts, like, can you trust like translating what we learned from global circulation models from observations from phase curves, for instance, to these morning and evening depths? They're like very careful with that because of this. So as the Germans will say, is the jein, like maybe, yes or no. Like we don't really know. But that's a good starting point though.
Thank you.
Okay, well, I have just a question, a simple question or not. I was wondering on what you mentioned before at the starting of your talk about there is no one abundance of water, and now with this kind of observation, everything changes now, because actually you cannot talk about an abundance, and because this. But let's be honest, this introduced a lot of complication. Let's say you got more data. So what's now your water abundance? Let's say with all the information, what's the? I don't know if you understand my question. What is now what you are looking for now that water abundance has not really a meaning now if you have this kind of data?
Yeah, I think that's a very, very good question. Like you're asking, like, how are you gonna make a plot now, like the one you show with the mass and the metallicity? Now that you have like now two abundances, and what if within those morning and evenings there's more little abundances in it? Like, what are you gonna do with that? That's an excellent question. My take on this is that it's gonna be an interface between modelers and observational folks. I'm more, of course, more of an observational astronomer. I like to delve into the theory, but I just do it for fun. Like there's real folks out there that do it for life, and I think it's gonna be an interface between this. So I envision a future in which I get you like a morning and evening cloud properties, abundances. Then you go, and as Rinaldo was mentioning, you go and measure circulation through phase curves, and with all this information, I tell you, okay, let's try to model all this with like a joint model with everything together. And with that, you have to ingest an abundance to those models, right? You have to define, how many atoms of helium, hydrogen, carbon, oxygen, etc. you have. And with that, you can start claiming stuff about the abundances. And that's the way I think that we should approach this. It's a very complicated thing, I take it. It's going to take years to develop this mechanism. But I think that's the only way in which you can truthfully do something like that.
Yes, I agree. I think it's going, I don't know if the comparison I am doing is okay, but it's moving very, very far away from spectroscopy from a star now, because we can get so much information.
Yeah. The fact that they're 3D, it's complicated. Yes.
Yes. So, Rinaldo?
Néstor, in fact, it's a question from Samira Shahad Ehlers. She's following your seminar via YouTube. So she wrote, congratulations, Dr. Espinoza. Can you predict the atmosphere in the middle i.e. in the penumbral belt using evening and morning assumption. She's biologist.
So can you predict what? Can you repeat that part? Or maybe write it down.
Can you predict the atmosphere in the middle, in the penumbral belt? In fact, I'm not familiar with what is penumbral belts. So using
Maybe
your model
write it
of
down.
evening and morning assumption.
But I think I'm having troubles with hearing the question. It's more of a sound thing other than.
Okay. I will bring
Maybe.
this question to the chat.
Yeah, I mean, if you move it to the chat, I can read it.
Yeah.
Oh, in the penumbral belt, using evening and morning assumptions. Oh, that's an excellent question. In the middle, yeah, that's kind of well, moving away from the morning and evenings, like moving beyond that. That's a big question. In theory, you could, but you have to build like a sort of a different model, like a more little detailed model, I would guess, in the atmosphere. And I can go beyond that question from Samira in terms of like, can we predict polar abundances even? Like, it's the morning, and then this might change in the poles, and you can build a model like that. I think that would be the next step. I've always looked at this morning and evening fits like as the first approach, first order toy model. But then it will be really, really nice to do like a much better model, much more complicated eventually once we detect it. But we first want to detect it and then jump to these very interesting questions like the one that Samir was asking. Yeah, yes, it's a definitely very, very exciting and important question to answer. Yeah.
Okay, Beth?
Okay, Nestor, going the line of some of the previous questions regarding the distribution, the temperature distribution, and therefore pressure distribution that makes this mixing and the heats the evening side of these atmospheres, exoplanet atmospheres. May I ask you, what is the current progress of modeling of atmospheres in these planets? What is because I think theorists, modelists of these systems can borrow a lot of ideas and and predictions from theoretical and observational work from stellar atmospheres, and also even our own planet, the Earth atmosphere, right? And because all this cycle and temperature distribution is related to convection motions, and so can you tell us a little bit about the current progress on numerical modeling, three-dimensional numerical simulations of these systems?
Yeah, yes, definitely. This is an excellent question, and I could speak for hours about this. But at the bottom line, I think the comment that you made, like, this has been done for stars and for the solar system. Yes, people are using these models, and for instance, for the hottest exoplanets, the ones that are about like 2500, we call them the ultra hot Jupiters. We just make up names in exoplanets, but for those ones that are very, very hot, people have been using, for instance, Phoenix models from stars, just modifying them a little bit to like work for exoplanets, and they work pretty well. Now, once you get down to color temperatures, it gets very tricky because everybody was mentioning before, like, clouds can enter some feedback that you don't actually see in most of the stellar models have like 3D structure. Maybe some of the brown dwarf folks have been working on this, but also the 3D global circulation models on that has been, they're very, they made the most out of what is available, but they're still primitive in terms of this feedback, right? There's progress being made on these 3D models with cloud feedback that, as I was just telling you before, it creates like a very different spectrum to what you would expect. And I've spoken with Emily Rauscher about this, and she's very excited about this morning and evening kind of work, because this is actually what the modelists need to tweak their models, because they predict like a wide range. As I was telling you, in the talk, I mentioned to you, like, there's modelers that predict that the limb difference can be very large and very small, and there's no consensus on this whatsoever. So constraints like the ones that we're showing are super important for them. Like even if we don't detect, even if we can only constrain, for them that's super important because they can say, okay, so the cloud feedback cannot be as big as X, because otherwise we wouldn't be able to see these small limb differences that Lauren was predicting in her plots that I was showing. So the state of the art is right now with global circulation models plus cloud feedback. And that's like very, very complex right now. Like it takes like a ton of computation time. I think we're approaching what the cosmologists have been doing with the universe. Like planets are their own little universes, right? Every planet is its own little universe that you have to model. And there's many subtleties, like linking now what you were asking about our own planet. Like there's the Earth in some manner, it's easier to model because you have this surface. And the surface has some impact on the atmosphere, like it adds like a boundary condition. For exoplanets and for giant planets in particular, that's not existent. You just have to define like a layer in which you stop doing your calculations beyond. And Ludmila Caron, for instance, has been showing that which depth you select for that, it's very important for the final spectrum. So there's like no limit into it. It's very complex, and you cannot simply take what has been done on both edges and join them. It's slightly more complicated than that. But again, there's excellent minds working on this right now. And there's many flavors of all the models that I've been talking about. So short answer is yes, people have been using the ends, but at the middle, it's very hard to just link them.
Right. Thanks a lot for the upgrade.
Okay, so I think there is no more questions. So we're going to thank Néstor. Thank you very much for your talk and for being here and for all this great discussion. Would you like to say something?
No, thank you. It was a privilege to be here. Thanks for all the questions. Like I love the discussion. And yeah, I hope I could get you a little bit excited about all this exoplanet work that is ongoing.
Yeah, so we are really hoping for the best for your observations coming. So yeah, you would have a lot of news in the next year. So this is awesome. So thank you again. And maybe we can end the transmission from YouTube. Okay. Okay.